This next section is a method of doing simultaneous material and energy balances on air-water systems. So air-water, we've already done air-water systems, and we've done a lot of calculations and we've done energy balances. But what you're going to see that this chart is designed to facilitate those calculations. So the chart is called a psychometric chart, and this chart has been the cause of students leaving chemical engineering and heading for chemistry. They said this was the last straw. So get ready. We're going to try to cover this, and if you get it, you'll discover that it's really quite easy to use, and it makes calculations on air-water systems easier. So there's a few new terms you're going to learn. In addition to psychometric chart, there's also wet bulb temperature, dry bulb temperature, adiabatic saturation temperature. And we've already learned dew point, but you'll see sort of graphically what that means. Humid volume, absolute humidity. And then the processes that we're going to look at in this section are adiabatic cooling and humidification. So again, what you're going to see is that this psychometric chart combines both material and energy balances for humid air. And this is useful for humidification operations, which it doesn't necessarily, I mean, that's not the only thing that chemical engineers do, but it's something that you should be aware of. And so anyway, you'll see next year you're also going to use this again in 160B. So this shows you a couple of examples of humidification operations. So in adiabatic drying, adiabatic, remember Q equals 0. So there's no heat exchange with the environment. Okay, there's exchange of heat between the air and the water, and that's how the process works. Okay, so in this case we have this is a dryer. Okay, this first one is a dryer, and we're going to do adiabatic drying. So you put in wet stuff like your blue jeans, and you want to take out dried stuff, and you put in dry air. Okay, and you take out humidified air. So the water, the hot air is blown over through the wet solid, and the water enters the air, and the air is cooled. So the water from the wet solid evaporates into the dry air. So this is drying. I'm sure you're all very familiar with drying. And this other one is adiabatic spray cooling. And I told you we were going to revisit this when we were going to look at the energy balances. We looked at the material balances, but we didn't look at the energy balances. So in adiabatic spray cooling, liquid water is sprayed into a stream of air. Okay, so we have hot air coming in, and we have liquid water coming out, and we have cool air leaving. Okay, so the purpose of this is to cool the air, and this is one way of doing it that is relatively inexpensive. Okay, so the water is sprayed into a stream of air. Some water evaporates into the air, which results in the cooling of the air, and then once the air is cooled, that water comes back out, because you cannot get as much water into hot air as you can get into cool air. So as the air is cooled, then the water condenses out. Now, some people don't like the psychometric chart. They like equations. So these equations come from the book that you're going to use for unit operations. So it just shows you how to do the calculations if you don't want to do them with the chart. But the purpose of this section is to learn the chart. So this is optional. You can learn these if you feel more comfortable doing the calculations And the other interesting thing about these equations is that you can then put them into the computer and do the calculations in the computer as opposed to having to read lines off of a figure. So, as you know, the water content in the air is quantified as humidity. Humidity tells you how much water is in the air. So this is defined, humidity is defined as the kilograms of water per kilogram of dry air, right? And this kilograms of dry air, now this is not a mass fraction, okay? The mass fraction would be kilograms of water per kilogram of humid air. Okay, that would be the mass fraction. So this is another definition. This is humidity, and this is this has this unique ratio of the water to the dry air. And you will see as we do these calculations why that is so convenient, that ratio. Okay, so you can calculate this using, this is the partial pressure of air. Let me just, no, okay, that's the partial pressure of water. Okay, so this is a bit confusing. This comes from Giancopoulos, but A in this case is water. Okay, so the partial pressure of water divided by the total pressure minus the partial pressure of water. Okay, and this is the molecular weight of water and the molecular weight of air. Okay, so these other ones, percentage humidity, we haven't actually used that one. There's the percent relative humidity. Actually, I think that's the one that we use for relative humidity. Okay. So now, when it comes to doing the energy balances, we have humid heat. Okay, the humid heat is the heat to raise the humid air 1 degree. And this humid heat has the small c with a subscript s, and it is the units are kilojoules. Okay, we're talking about heat, and here's that kilogram of dry air again times Kelvin. Okay, so this is like a heat capacity of the humidity. How much heat does it take to raise the humid air 1 degree? And this heat is this kilojoules, but it's defined with reference to the kilograms of dry air in the system. And this is this is for the air. This 1.005 is the heat capacity of, it's the amount of heat needed to raise dry air by 1 degree. So it's the heat capacity of dry air. Plus, and this is going to be the heat capacity of the water in the air. And this is H, which is the amount of water in the air. Then we have humid volume. Okay, this is the specific volume of humid air. And this one has units of meters cubed of humid air per kilogram of dry air. Okay, again, this meters cubed is for the humid air, but it's presented in this ratio with kilograms of dry air in the denominator. Okay, so the total enthalpy is going to be the amount of heat in the dry air. So it's not a heat capacity, it's actually the enthalpy. So it's, again, kilojoules per kilogram of dry air. And this has this ratio. This is going to be the humid heat, and T is the temperature of your air. T0 is the reference temperature. And H, again, is the amount of water in the air, and this is the vaporization enthalpy. The delta H of it, lambda 0 is the delta H of vaporization of the water, okay, which has been vaporized into the air. Okay, so this is just a simplification down here. Okay, so these all come from your Giancopoulos book. Now let's see what we can do with our psychometric chart. So the psychometric chart has a lot of features, and don't let the lines drive you nuts. Okay, what I want to show you first is let's find a point on this chart. Okay, so we're going to use as an example air at 50 degrees C containing 2.44 weight % water. Okay, so now we're supposed to find the wet bulb temperature, the relative humidity, the dew point, and the specific enthalpy. Okay, so this 2.44 kilograms of water per kilogram of humid air is the weight %, like I said. Okay, so what we want now, so we have here our air has 2.44 kilograms of water divided by 1 minus 0.0244 kilograms of dry air. Where did this come from? If you have a kilogram of humid air, okay, if you have a kilogram of humid air and it has this much water in it, then the amount of dry air is going to be the kilogram, 1 kilogram, minus the amount of water, and that's how much dry air there is. So if you make that calculation, you find out that the humidity, it's over here, moisture content, which is also the humidity, is 0.025. Okay, so now I've shown you this line on the chart. Okay, this is 0.025 kilograms of water per kilogram of dry air. So the line here is on the chart, and now the temperature is 50 degrees. We were given this. The temperature of the air is 50 degrees. So now that means that the blue spot here identifies that state on our chart. Okay. All right, we're going to learn more stuff here. The wet bulb temperature for humid air is the same as the adiabatic saturation temperature. Okay, wet bulb is the same as adiabatic saturation temp. P. Okay, beautiful. Okay, so you can learn all this actually reading the book, but I'll try to explain this to you this way. Okay, so the adiabatic saturation temperature is found. Okay, this is our state. So we're going to just ride up these diagonal lines. And those diagonal lines are the adiabatic saturation lines. Okay, and what that means, this is the enthalpy at saturation, and these lines are lines of constant constant Q. Okay, so there's no loss of heat. Okay, as we go up those lines. All right, so now so if we found the wet bulb temperature, so how do you find the wet bulb temperature? You ride this all the way up, and this line here is the saturation. This is when the air is saturated with water, okay, on that curve. So if we go up the adiabatic saturation lines to that saturation curve, then we find this dot, and we can read the temperature. Okay, so here's 30, 31, 32, and this would be 33, so we're almost at 33. So I picked out 32.9 degrees C for the wet bulb or adiabatic saturation temperature. Okay, then at that point also we can see the relative humidity of our air. Okay, here's 30% relative humidity, and here's 40% relative humidity, and we are somewhere in between. So this is about 31.8% relative humidity. Okay. So the dew point we read off the orange line. Okay, so the adiabatic saturation temperature, we go up the diagonal, but for the dew point we stay flat. And this, remember how I told you that the dew point is a measure of the amount of water in the air? And this shows you exactly, because here on this axis is the moisture content, the humidity. And we go all the way over to the saturation point, okay? And this is the temperature at which that air will be saturated. And we read that down here. So our air is 50 degrees. The wet bulb temperature is cooler at 32.9. And the dew point is the point at which that air would be saturated, is cooler yet. So it's about 28.7 degrees. Okay, and the last thing we can learn about on this is the enthalpy of our air. Okay, so the way enthalpy is read is you read it off of, this is the enthalpy at saturation. So we have to go all the way over here and find this. Now this yellow dot is above 115. Okay, so this would be 110, 11, 12, 13, 14, 15. And our air is higher than 115. So it's about 116.5. Then we have to subtract the enthalpy deviation. The enthalpy deviation is these curves coming this way, okay? So our enthalpy deviation for our air is going to be between this one, which is -1, and this one, which is -0.8. Okay, so we're between -1 and -0.8. Nope, I'm wrong. We're on the other side of the -1 line. Okay, so here's the -1, and the next one is -1.2. So we're not quite a quarter of the way, but so I picked out -1.05 as our deviation from the saturation. So that gives us about 150. The resulting enthalpy of our air is 115 kilojoules per kilogram. So if you want to look in the book, there's an excellent description of everything I just told you. So I would actually urge you to look at that section in the book and study the different pieces of information here, and see that the description in the book will help you find those points. Okay, so we could do all of these calculations with our enthalpy, with our equations, and I'm not really going to talk about this, but it's in the reader, and you can read these instructions if you want to use the equations. All right, so now let's talk about the next step, adiabatic cooling. Okay, so if the air we just calculated the specifications for is cooled adiabatically in a condenser to 10 degrees, determine the absolute humidity and specific enthalpy of the air leaving the condenser. All right, so our air leaves saturated at 10 degrees C. So the humidity, okay, of our air is saturated at 10 degrees C. So we are going to find here 10 degrees C, there it is, okay, and saturated. So now what is going to be the humidity of our final air, saturated at 10 degrees C? We can ride that line all the way over and see it's below the 0.008. So it's about 0.0077. So this is the final humidity of our air. And we found that the initial humidity of our air was 0.025. So we can see how much water is being removed. Okay, so this calculation shows if we were to use the equations, okay, we would find that we get about 29.5 kilojoules per kilogram. But we can use the we can find that we can do the energy balance on the air, okay, because we have the humidity. We have the enthalpy of the final air, okay, and it's here. It looks pretty close to 30 to me. And the initial one we said was 115. Okay, so we're doing this 115.1 minus 29.5, which I calculated using the equation, so it's very accurate, whereas I guessed it was about 30 looking at the figure. So our delta H is 85.6 kilojoules per kilogram dry air. All right, so now we can just figure out if 400 kilograms per minute of dry air enters the process, then the heat removed must be m dot delta H. So here's the delta H, and here's the m dot, and we have a final rate of cooling to be 34,240 kilojoules per minute. Okay, so, and the rate of condensation must be that this is the initial humidity, and this is the final humidity. Okay, so this is how much water is coming out, and that is going to be in kilograms of water per kilogram, and that's kilograms of water per kilogram of dry air. This is kilograms of dry air. And we're going to multiply it by the flow rate of dry air, and that gives us 6.92 kilograms per minute. Okay, so that's the lecture, and you can try to do this video quiz. You're going to look on the figure, and there's going to be air at 45 degrees C, and that's read off the bottom, the horizontal axis on the bottom, 45 degrees C. Find the 10% relative humidity line. Okay, it's to be humidified adiabatically to 60% relative humidity. So use the psychometric chart to estimate the adiabatic saturation temperature of the air. So I'm just going to show you on this diagram so basically what we're going to do here. Okay, it was our initial air is 45 degrees and 30% relative humidity, and we are going to humidify it adiabatically to 60% relative humidity. So first we're going to find the adiabatic saturation temperature, which remember is the same as wet bulb temperature. And then from there, once you have the final temperature, we have to determine the rate at which water must be added to humidify 15 kilograms per minute of entering air. Okay, so I'm giving you a hint here. For this problem, find the initial state of the air on the psychometric chart, then follow the adiabatic saturation line up to 60% relative humidity, and that will be the final state of the humid air. So let's look at this on the diagram. Okay, so we found our air, 30% relative humidity and 45 degrees, and we're just going to go up these lines to 60%. So this is going to be the final state of the air in that problem. Okay, so now you're going to do a few calculations on it, and how you can get the initial moisture content coming over here and the final moisture content coming over here, and we can look at the enthalpy. We can look at well, I guess that's pretty much all we need. Okay, so good luck.